So, in continuation to our discussion, this is uh, would be officially the last interaction we would have under the head of this particular syllabus is network theory. So, today we are going to wind up the remaining topic of, in one way, the kind of revision of the assets we discuss under the head of filters. And with this, I will take at the last the final stage of this particular session. I will take some lecture questionnaires from your end, and with that, we are going to conclude this particular syllabus. So, as far as the filter design aspect is concerned, to continue to our discussion, here we are going to consider the three different aspects, that is the output impedance of the filter, that is the values of and alpha and beta, okay, that is the attenuation constant and the phase constant, and then the revising the classification of the filters are concerned. So this is the most important aspect of our today's lecture series discussion. That is, let's say if the Z naught, as you can see, is given by root over of B by C, a particular filter. So B, you know, is a transmission parameter, and its ratio is delta Z by Z1, where delta Z is basically Z1 Z2 minus Z1 to Z2. Okay, symmetric component minus the reciprocal component, product of the symmetric component and the product of the reciprocal component, and that difference delta variation in Z, whatever you will get, that you can opt from here, where C is equal to 1 upon Z to 1. So if you are going to get the ratio of these two, root over that is going to represent by the Z naught. Okay, so equation 2, if you will substitute these values, you are getting root over of Z1 Z2 minus Z2 Z1. Now, if you are going to consider these two port parameters Z11, Z22, Z12 and Z22 in terms of the impedance of the network impedance or the arm impedance of the filter, that is Z1, Z2, then the interrelationship are Z11 should be equal to Z22. That means when it is going to satisfy the symmetric condition, in that case it should be equal to Z2 plus Z1 by 2. So the condition of symmetricity should satisfy the right half side of the equation, that is Z2 plus Z1 by 2. Whereas whenever the circuit is going to satisfy the reciprocal condition, then that should be equal to Z2. So remember, filter is one of the class of the circuit, special class of the circuit, which satisfy both the conditions at the same time, the condition of the symmetricity and the condition of the reciprocity. Okay, because you have a two different range which is used to meet the which either allow the signal to pass through it or reject through it. That is, I am talking about pass band and the stop band. Okay, with the help of deciding the two cutoff frequencies F1 and F2. So therefore, your transmission amount of impedance Z naught T is equal to root over of in terms of Z1, Z2. So your two port parameters are going, or quantities are going to replace by the more easier, because remember there are four different quantities and here I have only two numerical elements. You can say that one is the series element and one is the shunt element. So it is in terms of Z1, Z2 is represented as root over of Z1, Z2 within bracket 1 plus Z1 upon 4 Z2. So remember, now again this term Z1 upon 4 Z2 has comes into the existence. Okay, so therefore let us say for the better understanding, you can say, so as far as this particular filter approach is concerned, if it is a pure reactance in nature, okay, so in case of if it is a pure reactance in nature, that means both Z1 Z2 should be equal to, okay, J form of x1 and x2. So where therefore you are going to replace the Z1 Z2 both in terms of reactive parameter, that is the L and C. So in that case, for any LC parameter, the transmission impedance can be represented by the equation number 5, okay, which designated the pass band of the network. Okay, so note that here as far as the Z1 and Z2, that is the series impedance and the shunt impedance of the filters are concerned, okay, are opposite in sign, and further it should satisfy the that transmission criteria, that is your x1 upon twice x2. There we have a z1 upon twice z2. So now it is x1 upon twice x2 should be again greater than -1, but should be less than 0. Okay, for the free transmissions. Okay, or for the lossless transmission, you can say. In okay, till the time you are going to, your spectrum is going to, or your circuit element is going to satisfy this condition, there will be no losses. Once you dissatisfy this condition, there will be a losses. Okay, so you will get the merit of both. Understand? I hope is this clear. Okay, so therefore whenever we talk about your transmission impedance Z naught T, it is always a real. Remember, okay, it is a resistive and it indicates by the R naught. Now I thought you got the condition clear that at the beginning when we started that y z1 product of z1 z2 is equal to r naught square. Okay, so it is designed in such a way to minimize the losses. Okay, now further the transmission network okay possesses also resistive load without the attenuation. Now in stop band what will happen? You are not going to satisfy that criteria. So your x1 upon 4 z2 will be greater than 0. So if it is so, then what will happen? Okay, so if z x ratio of x1 by 4 x2 is greater than 0, so obviously because practically it should be less than 0, so if it is greater than 0, so then your z2 is z0 is representing as pure reactive. Okay, because if it is less than 0, it is a pure resistive. So if it is not going to, if it is going to violate that condition, so it is a reverse of analogy. You will get the rather than resistance, you will get the reactance in nature. Okay, understood? Okay, similarly in case of stop band, if this ratio x1 upon 4 x2 is less than -1, it should be greater than -1. So if it is less than -1, okay, so in this case the product of x1 x2 and this whole factor 1 plus x1 by 4 x2, okay, both the terms are negative. Okay, that entire, that the whole equation 4 what we have discussed is negative in nature, and therefore the characteristic impedance is reactive in nature, whereas what it should be resistive in nature. Practically no filter, remember, can be perfectly reactive. There will be some losses, so it should be reactive. So then the magnitude of loss or magnitude of that attenuation factor or attenuation loss alpha can be only measured if it is a transmission free, and that criteria is satisfied between the two boundary conditions, that the ratio of z1 upon 4 z2 or the ratio of x1 upon 4 x2 should be greater than -1 but less than 0. Please be noted this. Okay, I hope that this idea is now clear to you. Okay, so to justify that, for to that output impedance of filter, now here we consider a pi filter. I would insist that we apply the theory of z1, I mean the parameters of or the quantities of the z parameters from the two port network. Okay, substitute it and try to get the value of z naught pi. Okay, so z naught t is representing the t section filter, pi is representing the pi section filter. Okay, so in terms of z naught t, do it. Once you solve this, okay, probably you have got a couple of minutes of time and you will be able to get it. So you must have noted a very interesting thing. Okay, that is that this property, okay, if you talk about this equation, this is a very important equation. So you can see, okay, this is a you as you can see, if I will highlight it properly, I am talking about this equation. What is this? The product of the impedance in pi network and the Z network is equal to Z11, Z22. That is the product of the series arm impedance and shunt arm impedance. That is why this statement proves that the any pi structure, okay, of the equivalent Z structure of a filter is always a complement of each other, is dual of each other. Understand? It's a dual of each other. Whether you consider the pi structure or Z structure, you will always get the right hand side equal. That is the product of Z1, Z2. Okay, and if this Z1, Z2, okay, should be further equal to R naught square, and you are getting that value only if this whole product is equal to R naught square. You only if the Z1 upon 4 Z2, okay, is greater than -1 but less than 0. Very important slide. Okay, now I have got, I hope that you got this condition, that in which circumstances you will get Z naught pure reactive and the pure resistive. So reactive component, whenever Z naught is reactive component, so it is talking about the stop band. No frequencies will allow to, no signals will be allowed to pass. And whenever Z naught is the pure resistive, it is nothing but it is indicating the pass band. That is the signals which is allowed to pass. Okay, extremely important. Okay, extremely important. I would insist that you always remember this final conclusion or let us go ahead. That is the classification of filter. As I've been told you, that is at the end of the discussion, we are going to the conclude our lecture series as far as the filter design is concerned. So we initiate with the filter characteristic of the filter and the classification of filter. So here we are going to conclude the in terms of the classification of filters. One way, that is based on the frequency characteristic. We classify the filter, that is the four category: LPF, HPF, BPF, and BSF. Okay, and in terms of the impedance response, depending on the series and shunt arm, we got the two type. One is the prototype, or in other words called the constant K type filter, and then there is a M derivative filter, where the T section, the series arm of the T section is the multiple of M, or the shunt arm of the pi section is the derivative of the m. Okay, and in from this analogy we have find the very important property that the product of z1 z2, that is the product of the series arm and the shunt arm, should be equal to k square, should be a constant. So that means that's why you're getting r naught, because r is from the resistance. Okay, so to have a perfect resistive network or the signal which is allowed to attain a pass band which is allowed to pass. Okay, otherwise no signal will be allowed to pass, right? And whenever you are not going to violate, whenever you are going to violate this condition, you will get the stop band. Okay, so again I repeat, your z1 z2 should be equal to k square, or you can set that r naught square, and this should be whole factor you can achieve in terms of z1 by 4 z2, and this ratio should be less than 0 but greater than -1. Till the time you are satisfying this condition, you are in the pass band criteria. That particular design will allow the frequency component to pass. Once you are going to violate this condition, in whether it is your z1, this factor z1 upon 4 z2 is the less than -1, or whether it is greater than 0, then you are switching to the stop band, which doesn't allow your frequency component to pass. So that's how the two cutoff frequencies f1 and f2 decides, and we are going to design any particular filter. Okay, so I would insist that this our discussion you also apply, okay, for the various structural design of the uh, mm, constant K type filters, whether it is a T structure or whether it is a pi structure. In this demonstration, previous demonstration in slide, I've given T structure. You can apply for the pi structure also. And how, okay, I would also suggest you to investigate that how the cutoff frequency, okay, which is a component of your LC, as far as the LC type filters is concerned, okay, is also can be represented in terms of gamma, alpha and beta, or how the component of alpha and beta, that is the attenuation factor and the phase factor, or the beta is the phase constant and alpha is the attenuation constant, are well relevant to the propagation constant, that is gamma, and this how the gamma is further relating with the pass band attenuation, okay, or the in terms of the pass band and the stop band. Okay, so with this, here I am going to conclude our discussion, that in which circumstances you will get your z naught t real or z naught t imaginary, that decides that whether the signal is allowed to pass. If it is allowed to pass, so within those two cutoff frequencies f1 and f2, it is called the pass band. Whenever it is not allowed to pass, that band beyond any that cutoff frequency, okay, that's how you basically able to find out the cutoff frequency of the filter, remember. Okay, or you can fix up the cutoff frequency of the filter, do the necessary mathematical modeling, and then you can decide the value of z1 z2 to attain that optimal value of fc. Okay, so this is a repetitive exercise. Okay, and with this you can mature a particular design, and whenever your z0 to become imaginary, that decides the attenuation band, and that's how you can get the value of f1 and f2, and within these two limiting band, anything which is a signal which is exist or the frequency component is exist is allowed to pass. So that's how you design a filter. With this, okay, we are going to end up. I hope that we had a wonderful discussion from the past couple of months of time, and uh, under the head of the syllabus we tried to touch the various aspects of the network theory. Okay, other than one of the important aspect, I would insist that the discussion is incomplete without the discussing the theorem aspect. But I hope that as far as the our VSSUT syllabus is concerned, we already have a sufficient idea, and or I would insist that you should brush up your fundamentals relevant to the network theorems, that is the superposition theorem, Thevenin's and Norton's theorem. The both are the complementing each other. Then the maximum power transfer theorem. Along with that, then the most popular is the reciprocal theorem. Okay, and with the some more theorem like the Tellinger's theorems. Okay, or the different kind of theorems whenever we used to come across under the head of different applications. Other than that, as far as the syllabus is concerned, we had discussion, tried to touch very fundamental aspect and different applications. In the module number 1, we talk about the self and mutual inductance with the primary focus over the transformer as a mutually induced electrical device or electronic device. Okay, used in various electrical and electronic applications. And then we touch the transient response, which is one of the one of foundation of one of the specialization in power system domains, that is power system transients. Okay, very important. It also touches the switching aspects, which ultimately relate with another specialization of the domain, that is protection and the safety or protection is relaying. Okay, and in industry also the protection and safety has the highest hierarchy, followed by the C&I, and then followed by the operation and maintenance record. Then we, in the under the other module number 2, we talk about the detailed discussion. We conduct detailed discussion under the head of the two port analysis, where we try to touch the four different parametrical aspects and their interrelationship, okay, to establish the interconnected network, to classify the complex interconnected network into the simpler part for the analysis purpose, and vice versa. Then we also see the circuit level aspect here we touch. Then we jump to the module number 3. There we see the system level approach, that is the network function of the transfer function and its conditions for the implementation or the constraints. Okay, with both the impedance parameter and the transfer function and the impedance function. Okay, transfer function is also sometimes recognized as the system function. Then followed by, we also discuss the at what circumstances you will be able to transfer the power, healthy power, okay, particularly in terms of power aspect as far as the three-phase circuit is concerned. Then we jump to the that is called the graphical approach of the analysis, that is the graph theory. Okay, and for the filter design aspects. And at the end of the day, we also conclude the module number 4. Although some authors they prefer to go in series, there is no harm about it. As I told you in the beginning, like some of the academicians, they also try to trust the graph theory at the very beginning and then start the mathematical modeling approach, because mathematical modeling and the graph theory both supports the network analysis. Okay, whether the circuit is simpler, whether the mathematical modeling can sufficiently handle the network analysis without introducing much delay. If it is doing so, then jump to the graphical approach, though they are the two different approach, but both supports the network analysis. Whereas the network synthesis part, and in the under the order of network synthesis, we primarily see that how to design a white box, how to design a circuit to have having known input and the also known desired output. When the your expectation, that is the response, is predefined and the type of inputs are already known, so to meet these two criteria so that you can get your desired output, you design the circuit. Okay, this whole analogy is called the synthesis, network synthesis. Whereas in case of network analysis, what we do, the network itself, the circuit itself as a white box or the black box is known to you. I would say that rather it is a white box rather than black box. And now depending on the type of input, you try to judge the characteristic of the circuit analogy in terms of the response of the circuit. That is the network analysis. That is the fundamental difference between the network analysis and network synthesis. Okay, again I repeat, it is one of the fundamental subject as far as whether you talk about your higher whether you are preparing for your the job, okay, or whether you are preparing for to meet the requirement of to upgrade your degree, okay, whether you are approaching for the higher education, something like you are trying to qualify the gate examination, okay, graduate aptitude technical test conducted by the IITs, or whether you talk about your public sector exams, you wanted to lay your career in the electrical science domain, whether you are in the electrical field or the electronic field, that is the high power field or the low power field, okay, high voltage field or the low current applications, it doesn't matter. Network theory and or in other words network analysis and synthesis lays one of the foundation subject, and without which the perfect foundation of the electrical sciences is unimaginable. Okay, so with this I hope that you enjoy the lecture series with me. If still you have any doubt related to any module, okay, never hesitate to contact me at the given email address. Okay, and we can pursue. I will try to clarify your doubts, and I hope that with this you are looking forward for your next semester. Okay, and your lay a perfect foundation for your higher education degree as far as the electrical science domains are concerned. Okay, so with this, thank you very much. Okay, to go through my entire lecture series. Good luck.